We now consider the acid-base properties of amino acids. And to start with, I want to tell you that the structure I drew in the previous lesson is actually wrong. I drew the structure of an amino acid with an amino group and a carboxylic acid group. But actually, at pH 7, amino acids exist as Zwitter ions. Okay, a Zwitter ion is a structure in which you have both a positive and a negative charge in the same structure. And they exist as Zwitter ions because the amine nitrogen has a positive charge and the carboxylic acid oxygen actually has a negative charge. It's because the amine nitrogen is protonated at pH 7 and the carboxylic acid oxygen is deprotonated at pH 7. And that, of course, is due to the fact that the amine is basic and the carboxylic acid is acidic. So let's explore this in a little more detail. So for amino acids that have neutral side chains, which is the majority of them, there are two acid-base equilibria that we have to be concerned with. First, there's the acid-base equilibrium of the carboxylic acid losing its hydrogen, and then there's the acid-base equilibrium for the protonated amine losing its hydrogen to give a neutral amine. So in general, there'll be a table on the next slide, but the pKa of the carboxylic acid is generally between 2 and 2.5, and the pKa for the protonated amine is between 9 and 10. So what that means is that at low pH, the pH is below the first pKa, the molecule exists primarily as a cation, which is what's shown on the left. At pH values between the two pKa's, okay, so that's roughly between 2.2 and 9.4, the molecule is neutral overall, but as I said already, it forms a Zwitter ion. We have a positive charge on the nitrogen and a negative charge on the carboxylate oxygen. And then at pH values above pKa 2, the nitrogen is neutral, but the overall molecule still bears a negative charge because of the minus charge on the carboxylate oxygen. So what about if the pKa equals the pHs? Well, when the pH is equal to the first pKa, the concentration of cation on the left equals the concentration of Zwitter ion in the middle. And when the pH is equal to the pKa 2, the concentration of Zwitter ion is equal to the concentration of anion. So all of these principles that I just gave you are the consequences of something called the Henderson-Hasselbalch equation, which is something you learn about in general chemistry. One other note that I want to make is that the carboxylic acid pKa, you might have learned earlier in the course that carboxylic acids have their pKa's in the 4 to 5 range. And I'm telling you here that the pKa of the carboxylic acid is in the 2 to 2.5 range. The pKa is unusually low for the carboxylic acid because of the inductive effects of the alpha amino group. Okay, so the nitrogen wanting to pull electron density towards itself stabilizes the extra electron density on the negatively charged oxygen, and that is in fact even more pronounced than normal because that nitrogen is positively charged and really wants to pull electron density towards itself. So an important number associated with amino acids is what's called their isoelectric point, or their pi value. And the definition of the isoelectric point is simply the pH at which the concentration of Zwitter ionic form is highest. Okay, so how do we go about calculating that? Well, the answer is that the pi for something with neutral side chains is simply the average of the two pKa values, pKa 1 and pKa 2. Because, as we have seen, the Zwitter ion is what exists between those two pKa values. So if we want to consider alanine, its pKa 1 is 2.34, its pKa 2 is 9.69. So if you take the average of those two numbers, you get 6.02. So for most amino acids, the pI is around 6. So what that means is when the pH is above the pI, you have an excess of, well, you have some of the anionic form, not an excess, but some of the anionic form present in addition to the majority of the zwitterionic form. And that is the case for most amino acids at physiological pH, because pH 7.4 is above the pI value, which will be around 6. But now you notice that for some of the amino acids on this table, there is another pKa value for what's listed as the side chain. So aspartic acid, glutamic acid, cysteine, and tyrosine actually have somewhat acidic side chains. Aspartic and glutamic are the ones that are appreciably acidic. The other two are very weak acids. And histidine, lysine, and arginine have basic side chains. So the pKa values listed in this side chain column have to do with the acid-base properties of the side chain. So we will consider an acidic side chain and then a basic side chain in the next 2 slides. So when you have an acidic side chain, as you saw on the last slide, there are 3 acid-base equilibria, and as a result, 3 pKa values. So if we consider glutamic acid, at low pH, this exists as a monocation. Then as you make the pH more basic, you deprotonate one of the carboxylic acids to make the zwitterion. Make the pH more basic, you deprotonate both carboxylic acids to give a net monoanion. And then as you make the pH even more basic and past the 3rd pKa, the positively charged amine gets deprotonated, and that gives the dianion. So the pKa values for these 3 processes are 2.19, 4.25, and 9.67. So it's the carboxylic acid in the main chain that's the most acidic. The side chain acid for glutamic acid, being further away from that amino group, actually has a pKa value that's more typical of carboxylic acids in the 4.25 region. Okay, so the predominant form at a particular pH is the structure of these 4 structures drawn above between the 2 pKa values that bracket the pKa of interest. So normally the pKa that we care about is physiological pH, or pH 7. So the predominant form is the monoanion because it is at pH 7 is between pKa 2 and pKa 3, between 4.25 and 9.67. So as a result, at pH 7, amino acids with acidic side chains will be negatively charged. And then to calculate the pI, remember the definition of pI is it's the pH at which there's the greatest concentration of zwitterionic form. So in this case, the zwitterionic form exists at lower pHs. It exists as at pHs between pKa 1 and pKa 2. So therefore, the pI is going to be the average of these 2 pKa values. pKa 1 is 2.19, pKa 2 is 4.25, and the average of those 2 are 3.22. So that's the pI. And then, as I said previously on the last slide, cysteine and tyrosine also have acidic hydrogens on their side chains, but they're much weaker acids. The pKa 2 value is 8.18 for cysteine, and the side chain acid for tyrosine, the phenolic OH, is much weaker. Its pKa is 10.07, and because that's a higher pKa than the alpha amino group, that actually turns out to be pKa 3 for tyrosine. We can do a similar analysis for the amino acids with basic side chains. They also have 3 acid-base equilibria, and they also have 3 pKa values. So what you have to remember is for the nitrogen atoms on the side chain, we are actually considering the pKa of the conjugate acid. So let's look at lysine, just like we looked at glutamic acid. So at low pH, the two amines are protonated, and of course the carboxylic acid is protonated too. So you end up having a dication. As you make the pH more basic, you deprotonate the carboxylic acid first. That's going to give you the net monocation, in which the two nitrogens are still protonated. Then we deprotonate one of the nitrogens to make the zwitterion, and then finally, at very high pH, you've deprotonated both nitrogens, and you are left with the anion. So the three pKa's for lysine are 2.18, 8.95, and 10.53, and you should note from the diagrams that the side chain is actually a stronger base than the alpha amino group. It is the side chain that is the last to lose its proton. So at pH 7, amino acids with basic side chains are going to be positively charged because pH 7 is between pKa 1, 2.18, and pKa 2, 8.95. Therefore, the predominant form is the net monocation. So remember, acidic side chains are negatively charged at pH 7. Basic side chains are positively charged at pH 7. And for determination of the pi, once again, we have to average the two pKa values that bracket the zwitterionic form. So the zwitterionic ion here is bracketed between pKa 2 and pKa 3. Therefore, the pi value is the average of 8.95 and 10.53, which is 9.74. Okay, so with the basic side chain, you have pi values that are higher. With acidic side chains, you have pi values that are lower.